thesis was, I think, a step forward in understanding the dynamical state of stars, of the old population of stars in the galactic center. Today, he will talk about some other aspects of the galactic center. His talk will focus on the fast-moving object G2 at the galactic center.
Great, thanks. Thanks for the invitation. Today, I want to talk to you about an interesting object at the galactic center. It's interesting and sort of controversial at this point, but kind of unique in astronomy. We will actually find out the answer in like a year. So I think hence, will there be fireworks is going to be the test of this object. So this work I'm talking about today is based on a lot of Keck observations, and it's based a lot on this paper that we recently submitted to AstroPH. Okay, so to begin, what is G2? G2 was discovered in 2011 or so by Gillison et al. When they looked at objects that were moving fast to the galactic center. G2 is moving extremely quickly. You can see these are images taken at L prime, which is 3.8 microns, taken over many years. And you can see this object here, it's sort of faint in this projection. But so in 2003, it's here, and it's moving really rapidly toward the black hole. So the fact that there's a fast-moving source at the galactic center is already pretty interesting, because we're always on the lookout for really fast stars in the galactic center. In fact, one of these stars, SO2, right here, is the star that's used to measure the black hole mass and the distance to the galactic center.
The big yellow star is the black hole.
Oh, yes, the big yellow star is Sagittarius star.
And what's the star in 2008 that's on the yellow star? Is that just black hole brightening, or is that an actual star?
It's maybe a combination. I think there was a star that was here too. Yeah. As you can see, lots of things move around, right? So just the fact that it's moving very fast doesn't make it particularly unusual, but it could be interesting. What makes it really unusual is if you look at K-band. So the previous image I showed you was 3.8 microns. If you look at 2.2 microns, actually this filter is where we usually do all of our astrometry. It's here. This is why it was missed for so long, actually, because normally we only look at this wavelength, because this is at 2.2 microns, you have better angular resolution. And at the location of this object, at L prime, there is basically nothing. Okay, and then if you, this is basically a plot of the L prime positions on top of the K observations. So the limit that Gillison et al. Got was 17.8 magnitudes at K prime, that it couldn't be brighter than that. But the source is detected at L prime, so this applies an equilibrium dust temperature of at least less than 550 Kelvin. Okay. Further unusual things, G2 shows really strong hydrogen emission lines. Here I'm showing the continuum, and there's arrows supposed to point in G2, it doesn't exist. But if you look at bracket gamma, the line in bracket gamma, it pops up immediately. So this is an integral field spectrograph observation of G2, and so you can look at different wavelengths of this object. Here's SO2. Here's where the galactic center is, the Sagittarius star. Okay. Also interesting is if you plot the orbit of G2 against the position in the plane of the sky here in one direction. This is one particular direction they picked, and then this is radial velocity in kilometers per second. You see this is the object here, G2, and then there's this sort of extended emission behind it, which the authors attribute to be as a tail, a gas tail from the source, G2. Okay.
They don't feel it goes on further down.
What? Sorry?
Line curves around, but sort of by eye it looks like you could go on a bit further.
Oh, this?
Yeah.
Yeah.
Anyway.
Yeah.
Yeah, or even
There looks like some gas ahead of it. You mean? Yeah.
Yeah.
Okay. So The other exciting thing, of course, is that because it's so fast, it's going to go by closest approach to the Sagittarius star very quickly. At the time, in 2011 or so, when this astrometric point was taken, the closest approach was predicted to be around September 2013. So that's just a couple of months from now. Here's the orbit. Notice actually in the orbit, this will come important later, is that in the plane of the sky, the orbit is really linear. So it basically moves like a line straight at Sagittarius star. This has implications for how the orbit goes, basically. But anyway, so this was very exciting, and the authors proposed that it might be a gas cloud. So the idea is that this is a blob essentially that's not gravitationally bound, and based on the bracket gamma luminosity, they predict that the source is about 3 Earth masses or so. And so if you have a gas cloud of 3 Earth mass, and the size of the source is about 100 AU or so in width, then when you get close to Sagittarius star, the gas will be stripped off of the source, and you'll have an accretion on Sagittarius star, right? So hence, this is the fireworks, right? So at closest approach, we should see lots of activity on Sagittarius star. There could be, jets of things flying out. As it goes past the black hole and then falls back in, you're going to get an increasing accretion state for Sagittarius star for years, basically. And this will offer maybe a way of testing accretion physics. Right? We have all these models of accretion physics. Now we can watch it in action, which is not so easy in external galaxies. But
are such low mass clouds observed elsewhere in the galactic center?
Well, that's a question. Maybe we can wait till near the end. I'll address that question actually. Yeah, but I mean, feel free, everybody, to interrupt or give me suggestions. So I've made this talk such that there should be plenty of time for discussion. Okay, so one problem though with this gas cloud is if you have a 3 solar mass gas cloud without any gravitational support, how does it hold itself together in the galactic center? And there's many instabilities that can happen, and this is just one of them. This is called the Rayleigh-Taylor instability, and this is what happens when you accelerate a fluid of some density through another fluid of a different density. It quickly breaks apart. So this is just a nice example with jars and with water. So if you just drop some food dye into water, you can see the effects of Rayleigh-Taylor instability. And this should break up the cloud on the matter of within decades, even less.
What's the background density, roughly? Do we have any sense of what the background density is?
There are some estimates from the X-ray. It's less. Well, yeah. Okay. The other hypothesis is that maybe this is an obscured star, and this is a star in Orion. Actually, this is an HSC image of one of these proto-stars in Orion, and you can see that there's this very, very dark disk. So this could be responsible for the very redness of the source. And young stars typically also have outflows that would show up in hydrogen emission lines, or accretion would also do that. Anyway, the source has lots of excitement, and over 40 proposals from gamma ray to radio have been now approved to observe G2. And this is just a small list of them. You wouldn't go past this slide, but so there's a lot of telescopes about to look at this object, right? And so I think one thing is we should try to figure out as much as we can now about when should we be doing these observations and what way we should do these observations. And so the observation I'm going to talk about now is from the Keck telescopes, and these are primarily AO observations, so adaptive optics observations of the Galactic Center. This image is really faint now, but here are the Keck telescopes. Here are the lasers pointing at the Galactic Center. So we take images and spectroscopy of the Galactic Center. The images are taken, like I previously showed, at K-band, 2.2 microns, and then at L-band, 3.8 microns. So at 2.2 micron, you have an angular resolution of about 60 milliarcseconds, and at K-band, L-band is about 100 milliarcseconds. We also take integral field spectroscopy with OSIRIS. Here's this little instrument. And like I said before, with integral field spectroscopy, you're basically taking images at lots of different wavelengths. And that has an angular resolution of about 70 milliarcseconds and a spectral resolution of about 3,800. This corresponds to be about a velocity resolution of about 70 kilometers per second. Okay, so what does the data look like? Here are the L prime observations. This is at 3.8 microns. You'll notice immediately there's tons of dust, right? So this is from hot dust at the Galactic Center, and you can see that there's this is 1 arcsecond in the sky, which corresponds to about 0.04 parsecs or so. The Galactic Center, Sagittarius star, is right here where my laser pointer is. And you can see this big feature. It's called the mini spiral, and it's a big gas feature, gas and dust feature. And here's a big complex of gas and dust over here too. Okay. And then if we zoom in, we can see G2. Well, okay, maybe we can't see G2 in this. So the contrast is kind of poor in the projector, but it's right here. Anyway, so this is Sagittarius star here.
So, quick question: why is Sagittarius star? Why is it a bright spot? Is it lit in 3.8 microns, or is it some star that's just close to it?
It's lit. You can see emission from Sagittarius star at K-band as well.
It varies a lot, right?
It does, yeah.
Based on accretion.
Yeah. Yeah. It varies by over 1 magnitude over the night. Oh, this is a little better. You can sort of see a smudge here, right?
There's a lot of similar smudges. Are those noise or the other?
This will become important when I talk about the orbit. Okay. Okay. So now let's look at the gas structure. So we just saw the dust in the region and some of the stars. So definitely some of these are stars, right? Like this guy is a star. This guy's a star. Now let's look at the gas. So to look at the gas, I'm going to show a little movie of OSIRIS, the integral field spectrograph we use. So this movie that you'll be seeing, I'm stepping through different wavelengths. So that's different velocity channels near bracket gamma. And bracket gamma is the strongest emission line we see from this source in the near infrared anyway. And let's see, so this box is basically about the same field of view that these spectra are taken. And I've taken out the stars. So I've taken out the continuum for the stars. So all you'll see should be the gas. So we start out at minus something. So you can see like at different velocities, you see a ton of gas structure at the Galactic Center in bracket gamma. By the way, Sagittarius star is about here, which places it about here. So you see that actually where my laser is, there's like spots of gas that comes out. Okay. So this is just a still from the movie. This star down here is IRS 16 Southwest, and you can see the faintest traces of like a bow shock around it. Right?
Sorry, that's not an S star. That's something further away.
Yeah. So the definition of S star is sort of empirical in that we just call everything that is like less than 1 arcsecond away an S star. Actually, all the stars also have S designations, but typically when someone refers to an S star, it's within 1 arcsecond. So this is slightly outside of 1 arcsecond. So the S stars would be in this little region here. Yeah. But you can see that like stars, this is a Wolf-Rayet star, so it's not surprising that there's a bow shock in front of it. But I'm just emphasizing that there's lots and lots of gas structure, and particularly in bracket gamma. This is the region we're looking at for this source, right? Okay. So Linda's comment about the various blobs goes into this. So it turns out that if you do star planting simulations to figure out in that L prime image I showed, when you can recover a star that you put in your images, it turns out you can't quite recover it without systematic error. And so basically when we put stars where we think G2 is in the images, we recover them to these spots. And the reason is because if you look, let's see, if you look, you see how that there's this like really faint structure behind it? It goes on top of the structure, and so the position that you measure from the source gets offset by the background, essentially. And so using astrometry from L prime looks like it would bias your results. And so the approach we took then is...
How big is a pixel there? Sorry, how much is this in arc seconds?
Oh, a pixel is 10 milliarc seconds. So this is 10 milliarc seconds of bias, approximately. Yeah. It's really a lot for an orbit because our typical measurement uncertainty is about 0.2 milliarc seconds. So this is all dominated by systematic. Yeah. So fit for the orbit. So what we did was we fit for the orbit using both astrometry and the radial velocities from the bracket gamma line alone. So if you remember the bracket gamma strength of G2, it is quite separate actually from the gas. So at least the head part is about from 1,000 to 2,000 kilometers separate from the other pieces of gas. So you can generally isolate it pretty well in the spectroscopy. So we decided to use the astrometry, the location of that object relative to the other stars as computed from the OSIRIS cubes instead of using the L prime images, which was what was used in the past. And so with this, we get a different set of orbits, actually. The closest approach is now at 130 AU, which before it was at 190 or so. So it's getting closer, and it's becoming more eccentric, this orbit. The orbit is also now pushed to March of next year, so 2014. So here's just showing that. The eccentricity is 0.9814, which is really pretty high. And actually, this plot shows the difference between using L prime, so this using these images, versus using only the orbit derived from the spectroscopy. So in red is L prime, and then in blue is this new orbit. You can see that the orbit changed a lot. And
You already have a measurement, right? So you know that you're right or not?
sorry?
In the velocities, looks like you already, or is that not data points? That's hard. No, that's in the future still, right? Now there's little blue points when the two diverge.
Here?
Yeah.
Oh, I don't. There are measurements.
It's not
Yeah. So there are measurements in 2012,
Right.
and there are measurements in 2000. So the 2013 measurements are in, but I haven't fully worked through the data yet, so I don't have a point for 2013 yet.
Sorry, maybe I'm jumping ahead. That eccentricity seems extremely large.
Yes.
So I mean, it's like someone shot a bullet directly at the Sagittarius star. Does that strike you as odd?
Well, all of the S stars have very high eccentricity
Like
too.
that high?
I need to think about this.
Yeah,
I think
is 0.98.
I think
Okay, so
SO16
they're
is
not-
0.98, right? I forget which one is.
Alright,
Yeah.
I
Anyway,
realize the
the-
S stars are that
it's not. The eccentricity distribution has a lot of high eccentricity stars in the region.
I guess if you break them up from binaries, which is somewhat expected.
Sure.
Yeah.
But that's still very strange, right? Because this is not something you thought was bound, right? You think this is coming in from large radii.
Right.
Wait, so
So
that's what I mean. That's why it's, you know.
Doesn't make
Right. So I mean, if this is a gas cloud, it can only come in once, right? I mean,
Yeah.
no gas cloud can have this
And
eccentricity
it's
and
like
live.
it's been aimed perfectly though.
Yeah, but there's some gravitational focusing, right? It's not just a random location in space, like it will be attracted towards the black hole if you aimed it in some other direction.
Yeah, but there's a lot of bulge potential further out to
Well,
diffuse the gravity.
we'll get to actually the formation time for this gas cloud in a little bit, and then we can argue about it then.
This is the first pass.
Maybe this is a little early.
If it's a first pass.
Yes. Is it this object is bound, or can it also be a hyperboreal orbit?
It does not have to be bound. No.
What's the error bound on the eccentricity? Yes, I know that point 80.
Yeah. So this gets into a tricky point about the orbit fitting. So the orbit fit assumes that it is bound. The orbit fit assumes that it's bound, right? So there's a problem like trying to figure out what isn't bound.
Even your formal uncertainty will give you some sense about this.
Yeah.
Oh yeah. So these are the uncertainties in eccentricity.
Okay.
So it's not statistically consistent with 1 for multiple sigmas.
No, but that's 2.5 sigma or so. But then if you have a prior in there which says, hey, you're bound, then it's
So with this super high eccentricity, could it just be foreground object? Could you fit a straight line through it? So it's just passing near the black hole.
It's moving 4,000 kilometers per second.
Does any object do that?
Not that I know of outside the galactic center.
It's high.
But its velocity
That's
is,
like a
its velocity is changing.
Oh, it's
you see an
yeah. I mean I
Acceleration,
see.
acceleration.
I mean, yeah. Actually, acceleration brings me to an interesting point. This high eccentricity comes because when you look at the orbit in the plane of the sky, it's really linear, right? Like I said earlier. And in fact, only until very recently do we see basically acceleration in the plane of the sky. So it's basically really linear. And so if you try to fit orbits to lines, essentially, you will get extremely eccentric orbits. And so this orbit is all driven by the change in radial velocities. Yeah. So it will help when it goes past closest approach. All orbits improve tremendously when it goes through a curvature point, essentially.
Just to follow up, I didn't mean to say that it wasn't bound. If it's a gas cloud, though, you believe it's the closest approach. So the fact that you get 0.98 out of bound orbits, doesn't that suggest this is not a gas cloud? This is probably a star somehow. Wouldn't that be a...
Oh, well, it's not at closest approach yet.
No, I know, but wouldn't that be? I mean, that I would think that would be an argument that saying this isn't. So for some reason, this isn't a gas cloud.
I think that's going to be your conclusion. If I'm honest.
Yeah, it's hard to get around that. I agree.
So, can I ask one?
Yes.
On the table that you showed.
Yeah.
So why is the semi-major axis much less constrained than the eccentricity of the orbit?
Oh, because the semi-major axis has to do with the period, right? This has to do with where's the orbit?
Really, you just
here it is.
measure something which is well measured, but its eccentricity you divide it by 1 minus e effectively, and that is a very uncertain number, right?
Yeah. Oh, actually, one way to see it is actually how much of the orbit you have over what you think the period is, right? So this orbit only starts in 2002 or so, or 2003 to 2012. So let's say 10 years, but the period is like 275 years. So you have a very tiny portion of this much longer orbit, and so your uncertainty in the orbit becomes very large. So here is actually a plot in 2D of the orbit we get versus the orbit when it was initially reported by Gillison et al. And you can see that while the orbits are very close to each other, now, because it sort of has to be, because that's where the observations are, they diverge a lot, right? So the Gillison et al. Orbit closes like this, while the blue orbit is much larger, for instance. But anyway, the point of this slide, was there any other comments about the orbit? Yes, go ahead.
2013, seeing actually observed the paracentral passage. The evidence is their data can show the radial velocity distribution, the S-shape, just like you assumed in the previous slide, where you use the dashed.
Yeah, you mean here? Yeah, so there's a recent paper by Gillison et al. Which has some 2013 data, and they used the same method we did, which was to use bracket gamma astrometry and radial velocities, and they get the same closest approach, which is next year. So, but they think they see some gas that's already ahead, essentially. Yeah. Okay. So one thing, the interesting thing when you get these new orbits, not only the closest approach have changed, but the orientation of the orbit is different, and so the orbit I don't think is any longer consistent with this tail that I was showing earlier, and this is a frame taken at 609 kilometers per second, which is the peak emission from where the tail is. So here's the tail, here's where G2 is. This is in 2006, and the orbit is now here, and the tail is many pixels away. Okay. We also derive a new K-band limit. So with the Keck data, what we did was we found the location where G2 should be in our best in our best observations, basically. And then we planted stars at that location to see whether we can recover them. And so the magnitude is now at 20th magnitude. So the limit is 2 magnitudes now below what was found before. This means the dust temperature has to be even cooler if it's dust emitting at L prime.
There's exponentials for you. You only gained 50 Kelvin
Yeah,
for all
yeah.
this work.
Yeah. Okay. The other interesting thing is G2 is spatially resolved, so that, but it does not appear to change in size. So here's continuum, you see nothing, and here at bracket gamma, you see G2 come up. So this time I haven't subtracted the stars, so it's a little harder to see, but you can see that there's a source here. But if you compare the source to the size of a point source, you'll see it's slightly resolved at about 20 milliarc seconds. And over time, it doesn't appear in spatial domain in a way that the size has changed. Okay. There's also no evolution in the line flux of G2. So if you take bracket gamma, the bracket gamma line over G2 and integrate all the flux, you get a plot like this, bracket gamma luminosity versus time. This is from Gilson et al.'s new paper. They show that the different years basically have consistently the same flux. Okay. But the width of the emission lines, however, do change. So in 2006, you have a pretty narrow emission line. By the time 2012, you have a much wider emission line. So this may suggest some tidal effects. And in fact, tidal effects may already be in place in 2006. So this is a plot of the position of G2 as measured as a function of different spectral channels. So i.e. different velocity channels in the map. So red is more redshifted than more redshifted than the mean velocity, and blue is more blue shifted. You can see that it's moving toward, like basically it's the center of the flux. It's moving. It's closer to the black hole at redder wavelengths. I don't know if I'm making sense.
I apologize for not paying attention earlier. The cloud overall is moving away from us? What's the radial velocity?
Let's see.
Yes.
So it's positive rate velocity, so it's moving into the plane of the sky. Yeah.
So it's basically falling toward the black hole away from us.
That's right.
Yeah, so in a 3D, actually that's a good question. What is the inclination in a 3D sense? Mostly the plane of the sky? Or
Okay, now you're going to have to make me think about 3D. So there's these angle of variables, inclination, and position in a studying node you can get. So it's like, so in the plane of the sky, it's sort of like this, I think. Yeah. Yes.
Do you know what's producing the bracket gamma emission? Like, is the cloud being irradiated from the outside, or is it internally?
Yeah, that's actually debated. That's one of the debates. So the gas cloud model, it would be ionization from all the OB stars and Wolf-Rayet stars and things like that. But in some of the stellar model, it could be outflows or accretion onto the star as well. We'll get to that actually. That is an important point. Okay, so we are here now. Okay, yeah. So the different spectral channels appear to have a different center. Okay, so now we sort of I've summarized all the data that we have, and now we can go through some of the models. So I'm not going to go through all the many models, just some representative ones, and I probably won't do these models justice. If you're interested, I suggest you read the sources. Okay, so let's start with some gas cloud models. So the first model was presented in the discovery paper by Gillis et al. And they basically took particles and placed them at the location in G2's orbit that would have been in 2000, and with some velocity dispersion that they predict, and then they just let the model follow gravity and go. So there's no hydrodynamics; it's just particles. And so you can see that over time, these particles stretch as you'd expect as it gets to a black hole, and then it sort of disintegrates over here. And this model appears to follow the position velocity diagram pretty well up to the point where the observations were made.
But these things move in complete vacuum.
Yes. There's no hydrodynamics, just gravity. Yes. So, however, if you add in hydrodynamics, a lot of things happen. One is that the cloud has to be produced very recently to survive, as recently as 1995, in fact. So there's two major gas cloud models now being presented with hydro simulations. One is a compact gas cloud, which means that it's like a spherical cloud and small, and one is a spherical shell. So the two gas models I'm going to talk about. So one, they initiated in 1995 here, and the size is basically this circle here. And then the other one is a shell of gas, which they dropped in 1927 over here. Okay, so we can see what happens. So this is the simulation of a compact gas cloud. You can see as it gets towards Sagittarius star, the gas cloud gets pulled ahead, and then it sort of has these tails streaming out. These are some of the parameters they use for the simulations. They use a 3 Earth mass cloud. They use a density of 6 times 10 to the minus 19 grams per centimeter.
Very dense.
Sorry?
That is rather dense. Is that actually expected? That's expected from the winds and so on, right? The massive stars.
You mean gas clouds with this density?
No. Oh, is it the density of the gas cloud or of the surrounding medium?
The gas cloud.
Oh, okay. That's
yeah.
fine. Yeah.
The surrounding medium is like several orders of magnitude more, less dense, I mean. And they find that they had to put this gas cloud in pressure equilibrium when they started it in 1995. The reason is because if it's too high pressure, the gas cloud expands too fast, and then it overshoots equilibrium, and then it disintegrates. If it's too low pressure, it gets compressed, and then it also sort of disintegrates and stretches. And so this is the model they found that can best keep it intact and look like the observations by now. Okay, the other model is that you have this ring. You have this ring of gas that starts out at apoapse, and this ring then falls in towards the galactic center. And the ring sort of stretches like this. And then when it falls in, it should look like that. So this ring sort of follows the position velocity diagram if you use the old orbit that was derived. But if you use the new orbit, it doesn't quite work out. But it does make these multiple filaments. So maybe, I don't know.
Out of curiosity, where do they posit that the 3 Earth mass gas ring comes from?
People have thought of nova explosions.
Yeah.
I mean, sure, but then
Totally crazy. Although this one should at least be expanding if it's a shell already on its own.
Right? I mean, it
Yeah.
would be exploded or something.
So there's remember I showed you there's all these Wolf-Rayet stars
Yes.
right outside this region. By the way, this is like 1 arc second, so
But
everything here is S stars.
They tend to provide colliding stellar winds, right? So
Yeah. So the thought is maybe a colliding stellar wind from multiple Wolf-Rayet stars hit each other, loses all of the angular momentum, and falls in.
There's a Rube Goldberg cartoon in the making.
Yeah, so it could work if these were the models. So I think probably one of the hardest things to explain is like the instantaneity of these models.
It just requires a lot of fine-tuning.
Yeah.
Sorry, what's great about the ring? What's better than just the gas cloud?
it holds together. Well, it reproduces the position velocity diagrams better in this model. But if you don't think that the tail that was previously associated with this gas cloud is there anymore, then you don't need to explain all this other stuff.
You should be able to know whether that tail doesn't move.
It does not move.
Okay, well then it's not associated, right?
It does not move in Keplerian way, I guess. So like it just sort of stays there. But I mean, I guess to be. But I mean, this model also doesn't really, like, the tail sort of stays in place over here for a while, right? I mean, it's just still there. So. Okay. Well, let's hear the other set of models. These are some stellar models. So, one of the first stellar models considered is T Tauri stars. This is an image of actually T Tauri. I've never actually seen T Tauri. It's really cool. So it's a proto-star. It's the proto-star that we've named T Tauri stars after, and it's a star here. It really has lots of dust all around it, and so it's really embedded. And so one idea is that maybe one of these proto-planetary disks. This is one of those proto-planetary disks, and the reason that you see all of this bracket gamma emission is that you're photoionizing the disk of the source here. And then the distance where they started this model, the disk can be about 12 AU in size. So the tidal radius of such a star, of a one solar mass star at a distance of 0.04 parsecs is about 1 AU. So you can have, so the disk has to be truncated at this location. And then as it goes in, the tidal radius gets smaller and smaller, right? So as the tidal radius gets smaller and smaller, more stuff can escape, and it's just going to expand. And so you should see basically an increase in bracket gamma luminosity as you get close. And this disk will not survive closest passage with the black hole because, as you can imagine, at closest approach, the tidal radius comes down to 1 AU, and so any disk would be ripped apart, or this kind of disk would be ripped apart. And so, this is just a bracket gamma luminosity. So they predict that this luminosity should increase with time. So several things that are problematic with this model. One is that we don't see bracket gamma luminosity increasing. And the other one, it probably has the same problem of instantaneous, like it can only go through the closest approach once, right? So that means it had to been orbiting the black hole somewhere in a nice normal orbit, and somehow got a kick such that placed it in this very eccentric orbit in the galactic center.
How deep inside is in the tidal radius? Like, what's the ratio between periapsis and the disruption radius in the two scenarios of proto-planetary disk and the gas cloud scenario? Is it close to the tidal radius? It's very.
Well, I think either of them can't go through closest approach, right? So it couldn't have come in, 200 years ago, more than 200 years ago.
Yeah, but I'm wondering whether the orbits could have changed, like.
Oh, you mean like the orbit changes slowly
Right.
until it becomes very eccentric?
In both scenarios, you just need one. You can only have one passage of the.
Yeah.
Okay.
Yeah. Okay. But there's also a different theory that also involves a T Tauri disk, which is that this T Tauri stars are mass losing. These young stars, we know they lose mass, and so they have very strong winds. And so these winds could cause a bow shock as it moves in toward the galactic center. So here's the diagram from Scoville and Burkert, and they see, so this is the envelope, and this is the ambient medium, and it's going through it. And so you get you light up the shock in bracket gamma, essentially. And since the winds arise from like below an AU, this object should survive closest approach. And this wind also could produce some gas at the end of the thing, so it could produce something that looks like a tidal tail as well.
Why do you still need a T Tauri star at all in this case? Just to hide it?
It needs to be obscured, yeah. Yeah. Remember, there's a big, like you need to account for the big infrared excess of the stars.
Do T Tauri stars have a dust envelope or a disk? Does it mean you have to have the right inclination angle to have it obscured?
I think they have disks, but they might have dust too. I don't know. Does anyone know?
Would disappear after a passage like this. That's gone, right? Even this doesn't change the fact that the disk will just disappear after this passage
because it's bigger than this.
The wind in the end comes from accretion, and the accretion disk is gone after a long.
Well, and T Tauri disks are like 100 AU in size too, so a lot of the disk had to have disappeared by now anyway, like where it is right now. Yeah.
I still don't understand why it has to be one passage.
This one doesn't.
Okay.
No,
This one's okay.
No, because after the previous passage, the whole disk outside of 1 AU will already be removed. You wait 200 years, there's no disk
But
left.
the orbit can change. Right?
Yeah, no, that's right. But you cannot have repeated
I
passages
see.
in the same orbit.
You still it can't be that red the next time it comes through.
Yeah, that would be you would think, unless the orbit changed. I mean, I don't think that's crazy in itself.
Yeah,
Can
actually.
you calculate how much the orbit would change by, like relaxation? Is it reasonable that the star had a further out orbit and now has changed that much that previously you would have had an intact disk and now this time you're going to chop it off to people than dynamic schedule or something like that?
No, they haven't. But I would guess that it can't even be at this radius. It can't even be at like 0.4 parsecs, 0.04 parsecs, because it can only have a disk of 12 AU at this distance, right? So, so it would have to have close. It would have to have periaps further than this distance first. I just don't know how the energetics work. Like, how do you change the eccentricity so much that it
Well, is it, I mean, this is kind of like disrupting a star. Like, if the star started out really far from a black hole, then in neither case does it have much energy, so it's just about angular momentum. And you just get a little kick from something, then you can change from having a fairly large periaps to having a fairly small one. You have to calculate how long does it take to change your periaps by a significant amount over an orbit to see whether that
Actually,
works.
there must be some finite probability that the orbit will change again before it goes to the axis, right? Due to
Because-
encounters with other stars in the stellar cusp or
Now
stellar black
it's
hole.
going really fast, such an arc. But if
Or
it's
are
far
they-
out, it's much easier to
Or that it
Yeah,
changed
yeah.
in the last 2 years or so.
I don't know. It's going at 2,000 kilometers per second right now. But yeah, I guess we'll see.
Let's see what there are other models where you could just be repeating this. That would be
Okay.
nice.
So the original model I liked,
Yeah.
which was that these are BE stars. So actually, I've been looking for BE stars at Galactic Center for a really long time, and I thought this was a BE star when I first saw the data. So what are BE stars? So BE stars is basically just like a normal main sequence star, but in emission. You can see emission lines, hydrogen emission lines, and about 34% or so of field stars are B emission line stars. And the Galactic Center has lots of B stars, right? All of the S stars are B stars essentially. So it wouldn't be that surprising to have a few BE stars. The reason BE stars emit is because they're rotating so fast that the gas from the two hemispheres basically gets funneled to the equator, and they collide, and they cause this shock, and the gas gets pushed out of the surface of the star, and so you get these things. This is a very highly exaggerated version, but if you take interferometric observations of BE stars, you see that they're highly oblate, like this. So anyway, depending on your viewing angle, you can see different line shapes. So in the infrared, they have these hydrogen emission lines.
So you see bracket gamma even in this as well.
Yeah, so they're very close. This is very close to the star, right? So you'll always see bracket gamma emission. And they will be red because there's stuff outside, but they're not as red as you would get T Tauri stars.
Yeah, can't make 500 kelvins out of that.
No, you can't. Yeah, I think that's the big problem. There are some very, very red BE stars, but I'm not sure why they are. I think it might be there are BE stars that have companions that are they're like mass donors.
So sorry, these are just too hot to make 500. Can you use a smaller star?
You can there are AE stars. You can have. It doesn't have to be.
They don't have very strong emission lines anymore, right? You need to excite this bracket gamma too. I think the mass transfer might buy you more.
Yeah. Anyway, there's problems with this scenario as well, which is what makes this is an interesting mystery, right? So it's hard. None of the scenarios I presented to you are particularly, I don't know. You guys at least don't seem particularly convinced that is the answer, right? Okay, so the question someone brought out earlier, is G2 a unique source? Oh yes, go ahead.
What is the estimate on the size of the object based on the angular size?
It's about 100 AU or so in diameter, I guess. Yeah. Okay, so the question is G2 a unique source? So this is an image I put together using K band and L prime. So L prime is in red, and then K prime is in blue. So you can see like infrared excess sources at the Galactic Center. G2 is here. Unfortunately, contrast is not great, but you can see it's sort of reddish, right? You can see all these other red sources, right? Sort of. By the way, this is G1. The reason why it's called G2 is because there was a very red source discovered next to Sagittarius star, and I guess it was called G1. So since this is the second red source near Sagittarius star that people discovered, they call it G2.
No G3.
Well, you can name these G3 if you like.
Not this G1.
Huh?
Not this G1.
It's probably a dust blob that is not. Well, it's very resolved, so it's probably more akin to all those dust structures that you saw earlier, and it doesn't have bracket gamma emission, so we don't know what the velocity is, and in the plane of the sky, it's moved a little bit, but only a tiny bit, so it's probably not next to Sagittarius star, would be my guess, but it's just a coincident thing. It's probably still in the Galactic Center, but.
What's wrong with an AGB star? It's also too bright, I guess.
It would be very, very bright. Yeah, an AGB star would make it impossible to observe this entire region. Yeah. And then, so some of these red sources, like this one, has no bracket gamma counterpart. This one is resolved. This one has a bracket gamma counterpart. A K continuum counterpart. And some of these sources have bracket gamma emission, and some of them don't. So G2 is up here, and then these three are some of the other red sources. So I think that there are sources that could potentially be like G2. So in terms of these T Tauri star arguments or other things, maybe the number density is not as problematic. If you have lots and lots of these sources, you might get some that are very fast moving toward the Galactic Center, possibly. Yeah.
Can you get anything from the alignment of bracket gamma? That would tell us how far from the source, how far from the star the wind is, if that's the correct model or something? For example,
Yeah.
all these sources that show bracket gamma emission, do they all have the same alignment?
I think by construction, they've made it that it does, because through the model parameters. But they don't necessarily have the same evolution in bracket gamma aligned with. I think that might tell you.
Yeah, I guess I meant for the different sources in the Galactic Center. Do they all have the different sources that show bracket gamma emission? Do they all have the same alignment?
They don't. You can sort of see in this plot, right? So G2 is here. It's definitely wider than say this line right? And probably wider than this line. Yeah, this is not a very. I haven't like gone through this in detail. This is just like my very quick like look through all the data.
Do you know if the line width is remaining the same for G2 all the time?
No, it's increasing with time. So that suggests some tidal effect for the source. Yeah.
Could it be a stellar merger? Mergers turn very red after.
Yeah, I was asking Linda about that, whether it could be a stellar merger. Like if it was a 3-body interaction with the black hole, like if it was like in a triplet, and then one flew away, and then the other two became more bound and merged as it came by bound around the black hole. This would explain the high eccentricity, but I don't know. Does it explain the very red?
Stellar merger to stars that merge close to the black hole. These objects usually become very red. Like there is these red null objects like BH monocerotis. They're all very red.
Because they have a lot of dust around them.
Yeah. After the merger?
Yeah.
Okay, so you can form dust after a merger from a merger?
You can.
Okay. That was my question to Linda yesterday. Okay, I see.
Observationally, you can.
Did you ask that?
Did you ask me?
He asked you.
He did, and I didn't.
You should ask
Sorry.
him.
Okay. Well, we'll ask you later. Okay.
This is observed. We have seen 2 stars merge that produced a lot of dust. No question.
Okay.
Don't care what the theorists say.
Yeah. Okay. Okay, well, someone should run with that. Okay, one last thing. What's happening with Sagittarius star, right? If we're going to expect fireworks, are we seeing it yet? The answer is not yet. The K-prime magnitude of Sagittarius star has not changed for the last 2 years. It's very consistent. By the way, the variability between this is probably just intrinsic variability of Sagittarius star. It can vary by over a magnitude during a night. So these are just the mean magnitudes. And I guess lastly, I'll just say stay tuned. We hopefully will find out pretty soon what this source is. And I thank everyone very much for listening.
Questions?
So the focus on a bound orbit and orbital elements seem to be somewhat misplaced, given that this object has to be formed only 10 years ago and will only complete about a 20th of an orbit. And it's not even clear to me that it's a bound orbit to begin with. So
Right, yeah. It would be definitely interesting to look at the non-bound case.
So
Yeah.
doing a orbital fit, assuming it's a hyperbolic orbit, would be interesting, I guess.
Yeah. I think an unconstrained orbit would be very interesting. Yeah, or our mechanism in which we've put the stuff into the crank is built for the stars.
What's the age of the T Tauri star? More or less 10 to 5?
The age of the T Tauri stars? I think T Tauri stars can have disks. Usually not many that have disks after 3 million years, but I think there are a few that do show disks after that.
So a few million years.
Yeah. So it could be consistent with that the young stars at the Galactic Center possibly generating some of these T Tauri stars.
And also with coming from outside the sphere of influence of the black hole.
Oh, I see. You mean to fling it on these very...
Well, that's the requirement to be
eccentric
unbound, right?
Yeah, but the requirement is not very different than for the S stars itself, which don't live that much longer, right?
Well, the S stars are B stars,
Yeah,
so they could be like
depends on
50 million years.
A bit longer.
Yeah.
Not totally crazy, at least.
Yeah.
So one of your data sets confused me quite a bit. When you measure the position in relation to the radial velocity, is that right? And you see it's elongated. That means like different parts of this object are moving at different speeds. Is this right? That means like it is some sort of blob-like thing. It must be pretty long by now. How close are these things in AU? The fastest.
Well,
and
no,
the slowest part.
the object. Oh yeah, I see what you mean. Let's see. You mean this?
Between the bluest and the reddish part, how big is this in AU?
Well, this is like 0.1. It's pretty big. Like 20, like I said earlier, 20 milliards-seconds I think was like 165 AU.
This thing is really massive.
Big.
Sorry. Colloquial massive. Big and.
And also, it's interesting that that this is not like it's not one feature. These two blue points seem very significant.
Well, these blue points, I think I won't believe. I think there's systematic uncertainties involved. At this, I didn't plot the observed brightness of these points. I mean, the central point is the most bright, and then it becomes less bright. And so this is just, yeah. And by the way, I mean these have like very large error bars. So.
And what's the difference in velocity between red and blue?
I forgot.
The resolution element.
Maybe 200 kilometers per second.
How long does
Did
it
you do
take?
it with better than a resolution element this time, Friday? Because you said your resolution is about 80. So presumably you didn't do it too much better than your own resolution.
To get the rate of velocity, we can get pretty precise, but this.
For this, you're measuring it on different slices. Presumably.
Yeah. So that's basically Osiris has 35 kilometer per second slices.
Okay, let's take the last question.
Okay, from the line emissions, can we infer the temperature of the emitting gas? From there, maybe we can make some diagnosis.
Yeah. So in the original paper, they estimate if you assume some sort of recombination mode, B recombination or something, you get gas temperature of about 10 to the 4 Kelvin.